Okay. Solutions. You remember your mixture stuff from chemistry 11 or science 10? Science 10, do you do mixtures? I don't know when you do mixtures. If you have a solution, so say dissolved in water, are we a homogeneous or a heterogeneous mixture? Yeah, or homogeneous, whatever you want to call it. Do you know what it means to say the solution is homogeneous or homogeneous as opposed to heterogeneous? Same. And so when you dissolve something and say it's a heterogeneous mixture, like a stew with big chunks of carrots and meat and stuff like that is heterogeneous because it's not completely uniform in how it's dissolved. Okay. But if you dissolve salt in water, it's uniformly dissolved or mixed, I guess. Mixed uniformly. Okay. Okay. So tell me solutions. All right. What's a gas solution? Just an example. It's in this room right now. Air. What did you say? I don't want to know what you said. Anybody know what is in air? You should all know one. That's the one? Okay, you're not wrong. I just thought oxygen was going to be the one. That is true. There is more. It's 78% to 21%. What else? Carbon dioxide. Ozone. Yeah, you could argue. Argon. You're just like saying stuff now. Helium. I guess if you were in a room that had helium dispersed into it, I guess there might be. We're gonna assume that these are the major ones. All right. What would be a solid solution? Sorry? An alloy. An alloy would be. All right. Brass. What's brass? What? Brass would be. Windows are a solid mixture. All right. Glass. Which is silicon oxide, sodium oxide, blah, blah, blah. There's other stuff. I'm never going to ask you to repeat this on a test, but what about a gas liquid? Most of you drink one of these every day. Sorry? I guess you could Starbucks. Gas and liquid. Bubbly water. That would be the best way. Or pop or any sort of carbonated drink. All right? All right. What if I said solvent and solute? Which is which? What do they mean? What's the solvent? Yeah, right. It does the dissolving essentially. It's the larger amount. So and the solute is what's dissolved basically. The smaller amount. Do we know what unsaturated, saturated, and supersaturated are? Do we know what unsaturated is? That is not wrong. Unsaturated means you could dissolve more if you're dissolving it in water. Saturated means you've reached the limit. You cannot dissolve anymore. What's supersaturated? You've actually gone past the saturation point. It's still dissolved in solution, but you haven't precipitated out anything, even though the math and the chemistry says you should. So you can have supersaturated solutions. So I will show you one next week. I tried to look for it. I couldn't find it. So no, what you do is, well, I guess you could do that. But one of the ways is you have a saturated solution and you cool it down quickly. And as long as you don't disturb it, certain chemicals will stay in solution, even though they should fall out. And then if you give them a shake, sometimes they'll fall out of solution. I'll try to make one next week. I thought we had some, and we probably do. I just can't find it. But or I can just make one. So I'll find one next week. Supersaturated is past the saturation point, and if you cool it down quickly. What do I want to say? I'll just say solute can stay in solution. What type of solution, saturated, unsaturated, or supersaturated, would be in equilibrium? Saturated. That's kind of what we did last chapter. If your trial KEQ, Michaela's favorite thing, all right, is calculated for an unsaturated solution, would its value be less than, equal to, or greater than the actual KEQ? Who says if you have, for an unsaturated solution, you do the trial KEQ? Is it going to be less than or equal to or greater than the actual KEQ? Who says less than? You don't have to raise your hand, I guess. That's kind of, who says greater than? Anyway, it's less than. Because you're unsaturated, right? KEQ is concentration of products over reactants. If you're unsaturated, you have more of this, right?
Because if you're unsaturated, that means that it's all.
You have more reactants. Like you can have more reactants. So your trial KEQ is less than actual. Therefore, what do I want to say? Therefore, I don't know what I'm trying to say. Therefore, you can add more. That's not the right one to say. I'm just going to say no, therefore. Trial KQ is less than actual. Dissociation. Kayla. But if you're saturated,
Because like the way I'm thinking about it, if you have water and you're putting stuff in,
yeah.
When it's not saturated, that means it's all products.
Yeah, but how many products do you have? The K, and you know what? The reactants aren't technically going to be there, right? Because it's a solid. Like if you think, okay, what do I want to say? If you're saturated, If you're saturated, it's all this, right? Okay. You can't add any more of that into solution. And KEQ is equal to, we say products of reactants, but this is a solid, right? If I'm dissolving salt in water. So we can really just look at this. KEQ is equal to products. If you're saturated, I can't get any more of this. Does that make sense? Okay. If we're unsaturated, I have less of this than I could actually have. Does that make sense? Okay. Disassociation. Basically, I just wrote disassociation. Disassociation, if you remember chemistry 11, it is the crystals of a solid break up into its ions. So in this case, I did one right there. Sodium chloride breaks up into sodium and chlorine, and I technically should write aqueous on them. So if looking at this example, what type of ions will dissociate, or what type of compounds will dissociate? You have ionic compounds dissociate. And then which ones don't? What's the other type? Covalent. Do we remember the difference between ionic and covalent? What's an ionic compound? What's the bond? What happens? Yeah, you get a donation of electrons, right? So it's the charge separation that holds them together. In a covalent molecule, what are you doing? You're sharing the electrons. And within covalent, there's two sort of different types. Remember polar and nonpolar, right? So you get a equal charge separation and then unequal charge separation. We'll talk about that in the second lesson. All right. Okay. Here's our ionic salts. Write the balanced dissociation equation for these things. In other words, break them up into their two ions. Do you have one? One of these sheets? And if we're doing it in water, I guess they should be AQ. You need to have the charges. So you should be able to, if you know one of the charges, you should be able to deduce the other charges, right? No, it's not important in the balancing of the number of atoms. Later on, we'll look at when redox chem, it becomes important, but. And you will start to use your data package in this unit more and more. We haven't used them much so far, but we'll start to use them more. All right. Does everybody agree with that? Sorry? It's a 3 on the lithium is what it is. Sorry. That would make way more sense. There we go. Mm-hmm. See, this is why I asked if everybody agreed with it. Okay, now is it right? Okay. I think I've talked about miscible. I've said that word, haven't I, in this class? Miscible, immiscible? Maybe not. Maybe I did in chemistry 11. Miscible means there's no limit to how much you can dissolve. You can mix them in any proportion. Okay? So no You can mix them and dissolve in any amount. All right, so like, I don't know, alcohol and water mix in any amount. Okay. Immiscible means they will not mix at all. What doesn't mix with water? Oil. That's an easy one, right? So, oil and water will not mix. In the second lesson, we look at why they don't mix. Well, this question I did, didn't I? If we talk about miscible in terms of entropy and enthalpy, that means it's all mixing, right? So we're going from, let's just say water in liquid, that's an L. Liquid plus, if I write ETOH, does anybody know what that means? No. That's ethanol. That's the alcohol you drink. ET is ethyl. OH is the alcohol group, if you remember your grade 11 organic chemistry. It's not, doesn't matter. So this is just alcohol. So if you're going to mix them, you just get a water alcohol mixture. I'm just going to write it like this, ETOH. Mixed. Okay, so what is delta S going to favor? The mixed or the pure form? The mixed, right? Because that's more random. So delta S is going to push this way and favor the products, because a mixed form is more random and everything tends towards randomness, increasing randomness. If we're miscible, so we can mix them in any proportions, which way does delta H have to be pushing? To the right as well, right? It's the only way it makes sense, because if delta H pushes back the other way, can it mix in any proportion? No, you're going to get an equilibrium. Okay. Delta H must favor, you don't need an E there, products as well. So if delta H favors the products, is this an endo or an exothermic reaction? It's an exothermic reaction. So you'd have plus heat or energy. Okay, does that make sense? Because if it pushed back the other way, then you're in equilibrium and it's not going to be a miscible substance. All right. Can I flip the page? Oh, sorry. Because these are pure. I got pure water, nothing in it, with pure alcohol, nothing in it. If you see the L's, that's pure form. Okay? This is them mixed together into a glass. No. You can't. But a mixed form is always more random than a non-mixed form, than a pure substance. Okay? Like, that's because when they're mixed, it looks like this. It's going to look something like this. Whoops. Like in pure water, you get this. We're going to look at this a bit. So remember hydrogen bonding? Right? Pure water, it's just water molecules all nice together. And same for the ethanol. As soon as you mix them, you've got ethanol I'll just put ETOH for shorthand. Bonding to, like, it's breaking up that purity, I guess. I don't know how else to say that. It's not just all water. You got ethanol that's in here. So they're both mixed together, which is more random than just the pure substances by themselves. Is that okay?
So for something that's
Immiscible?
immiscible, is it the opposite for delta S and delta H?
They'd both be pushing back the other way.
They're both favoring reactions?
Yes. I'm always hesitant to say like always yes, but yes, like it doesn't want to mix. Now there's reasons for that. We're going to look at the reasons actually a bit in the next lesson, 3.2, but and talk about those. But all right, solubility. Again, I apologize for just talking this whole time. What do you think? If I said the solubility of something is 5 grams per liter. Okay, so solubility is how much you can dissolve in a certain volume. All right. In other words, it's the concentration of the solute. All right. When substance is saturated. When I'll say solution is saturated. So there's 2 common units that we use for solubility. One of them, Jordan likes to draw them as a large lowercase m, also known as molarity. So moles per liter. That's a unit of solubility because it's telling you how many moles of something are dissolved in the volume. The other one that you will see is grams per 100 mils. Those are common ones. All right. Obviously, the grams per 100 mils is nice because if you have to weigh something out, you weigh in grams. You don't weigh in moles. Okay, so what we decide is soluble is kind of a relative term. If you look at your data package, I'll show you in a sec. The solubility, what they consider soluble, is 0.1 molar. Let me rewrite that. 0.1 molar. So in your data booklet, this table, it tells you right up here. The term soluble means 0.1 moles per liter at 25 degrees. Why do they have to give you the temperature? Because solubility is temperature dependent, right? Most things are more soluble in higher temperatures, but not everything. Okay? So it's sort of a relative term, and you need to know the temperatures. Okay. There we go. Next question. How does temperature usually affect the solubility? Does it increase or decrease it? It usually increases. There you go. So if you increase the temp, you get an increase in solubility, which means, I spelled Le Chateliers. So does that mean solubility is usually exo or endo? We've done this before. There's one question on your test on it. So if you increase the temperature, you shift the reaction to the right. So usually solubility will be endothermic, right? So and the reason it would be endothermic is because if you have, like, we'll go back to salt. and you dissolve it in water, if you ever do this in large amounts, if you feel the container, it should actually decrease in temperature a bit. It should actually cool down a bit, all right? Because it has to be endothermic. So energy is over here, right? Because if I'm adding energy, we have to push the reaction this way, which means we get more stuff dissolving. We've increased the solubility. I'm going to show you a reaction today, if we get to it, that is highly exothermic when you mix them together. Okay? If we have time, or I'll do it on Monday. It doesn't matter. Okay. I'm tired of talking. So, do you think you can answer these 4 questions? It's basically unit conversions. Convert the solubility of aluminum fluoride to moles per liter, and et cetera, whatever they ask. And then I can grab some stuff and we can talk about the next little bit. And the answers are there.